Hello everyone. In this lecture, we will focus on the use of graphics in reports and presentations. As you know, as you open different publications or manuals or even books, white papers and the like, you will find a variety of graphical aids that are meshed along the different pages of your report. And the objective of these different elements, these different graphical representations that you have on your report, they're there essentially to help the reader, the whoever is reading your document, to better appreciate and understand your work. Right. So in general, when we talk of graphics, we talk of plots. So you might have a plot that is two-dimensional. You might have a plot that is three-dimensional. Like the picture that you see here, right? So you see this plot here. It is also movable. So you have this kind of three-dimensional service plot, and you also have the projection of it in 2D, and this is known as a 2D contour plot. So essentially, it shows you the elevation of it. So it conveys kind of the same information in 3D, but also in 2D, and you have this option for a plot. And there are many other forms of plotting in two-dimension or in three-dimensional way. There's other methods known as scatterplot and many others, and we'll discuss some of them in this lecture. You will also find in your technical report, for instance, block diagrams. So in my field, in the field of telecommunications, we use block diagrams regularly. In other fields as well, and in control theory and in control systems, they use block diagrams as well. And it depends on the different disciplines. But the use of block diagrams is very useful, especially if you want to see your engineering from a system level point of view. So you could lump all the different components in a block and then look at it in that perspective with an input and an output, or multiple inputs and multiple outputs. You could also have your graphics in the form of an algorithm. So if you write an algorithm, that's essentially one form of presenting your data. You could also have the algorithm be translated into a flowchart, or go from flowchart to algorithm, or algorithm to flowchart. That these are also varieties of graphics. You could also have, of course, tables, drawing, pictures. These are all different varieties of different graphic methods that you could have in your report. And of course, the point of including these graphic is really to help your reader. And if you're doing this as a presentation, it's really to help your audience comprehend what your work is all about. Right, so you could put it in Word, you could put it with numbers, you could put it in equations, but it will be very, very hard to understand if it's not visual. And that's the point of this lecture. So many of the things that we will discuss could be considered common sense, and I hope it is. But we will still go through this topic, and the objective is really to make it more concrete for you. So let's go through through the different parts, and we'll begin with the next slide. Before we begin, I wanted to show you this quote from Napoleon de Bonaparte. He was the emperor of France and the ruler of France. This is his lifespan. He was born in 1769, and then he was gone in 1821. And he said, and I'll read it to you in French. Let me get my laser pointer. Un bon croquis vaut mieux qu'un long discours. So essentially, this translates to a good sketch is better than a long speech. Perhaps you've heard this form of it that we typically use in general in our society, that a picture is worth 1,000 words, to be attributed to Napoleon. And this statement is very powerful. It essentially tells you the power of having visual aids. So whether it's a picture or a graph or a block diagram or an algorithm or a flowchart or a table or any of that, they essentially, their purpose is to help whoever is studying the material to appreciate it in a much quicker way. put, it's again, it's just a statement. It doesn't mean it's always true. Ideally, you want to have both form, right? So you want to have some visual aid. You want to have a picture. You want to have a diagram, but you also want to have an explanation that comes with it. So ideally, you want to have both, not just a picture. But it tells you the power of having graphical aids. I'll show you an example. This is an example of how complicated information can be conveyed in a very digestible way. So in this case, on your x-axis, you have the income of individuals, and then you have the life expectancy of them. And then the different circles, it's not identified here, but I assume they're countries, and then they see how they move along with respect to years. So this is just so much information, but it's made in a way that you could comprehend it and digest it in a very little amount of time. So whoever did this would have probably spent many years working on it. In fact, one of the key people that brought prominence to this form of data presentation is the very famous Hans Rosling. So he was a physician in Sweden, but also he traveled heavily around the world, and he would be invited everywhere. But his home institution was in Karolinska Institute, which is in Stockholm, one of the leading schools in the medical area after Harvard Medical Schools and others. It's generally in the top 10 schools, and he was there. And this man. He was a data-driven individual, a person that appreciated the power of data and of making decisions based on data. And what he brought to the world essentially is how one can take data that is generally very static, and you cannot move it. You just take data and then you plot it, and it doesn't have a lot of. You cannot really understand what's going on. There is no story that could easily be conveyed. And then he took that and then he animated the data. And then suddenly you look at this data as a living object. It's moving, it's changing, it's dynamic, and it was incredible. I think he gave various talks, maybe including a TED talk, and then after that he became very famous. Everybody would invite him. He would be invited to different news outlets, including CNN and others, and he inspired many scientists, not only scientists working in the health sector, but also scientists as engineers to try somehow with their own kind of ability to take data and information that they like to convey, and then to bring it to life. One of the people that he inspired is like myself, yours truly. I'll show you some of my work that was inspired by Hans Rosling and how to present it. Okay. So in here, I wanted to show you some of my own work in the in connected and autonomous vehicle, and particularly we looked at V2V connectivity, vehicle to vehicle connectivity, as vehicles drive around an intersection. Most accidents happen at the intersection in this area here. Maybe I should highlight it in this area here. And so what we wanted to do is we wanted to see if you have an antenna on this vehicle and you have an antenna there, and you have these two vehicles talking to each other, and this is referred to as V2V communication, how is this impacted in terms of reliability? So we wanted to do that, and then we tried to animate these graphs to show this as the vehicle moved for the different iterations. And so this is kind of our own version of animating data that is usually very static. And in animating that, we were able to see that this is essentially the powerful graph that we were able to do. There's videos on this. You can find it on Vimeo that I uploaded, where it shows the trend here, where nothing really happens in the middle. It's either very bimodal. It's either very good or very bad, but nothing happens in the middle. And when you look at average reliability, it will be in the middle. So looking at it from an average point of view is misleading. That's kind of the idea of the work. But here my objective is not to really explain the technical content, but really to show you the the kind of our own little way of using data and trying to animate it in order to see more information and then to kind of perhaps appreciate it in a better way. If you just look at different snapshots, it won't give you the information correct properly. So in here, we try to vary the length of the roads. In varying the length of the roads, each of these roads, varying it, will certainly change the reliability of your communication, because the different variety of roads, the length of it, will have the higher concentration of interferers, and this will impact a metric that we have, the meta distribution, and that's kind of the objective here. And in here, perhaps you saw it earlier, now it stopped because I did it for 100 iterations. You saw that we did it for every different realization. So every realization of vehicles moving along an intersection, you would have one particular graph of the reliability, of the outage probability. And this is usually novel. People do not look at it for each realization. They look at it from an averaging point of view with equations. And that's kind of the major contribution that we wanted to show here. And by looking at it individually, the powerful component of it is that it's very bimodal. The average will be a line here, and then you can find it in videos if this is something that interests you. Whereas if you look at it individually, it's nowhere close to the average. It's either very good or very bad, but nowhere close to the average. And basically what we try to do in this work is to say that average reliability is not something that makes a lot of sense. It is in fact very misleading. Fine-grained reliability is the correct one. You need to look at it individually. And that's kind of the whole idea. But then again, this is not the purpose of this presentation. I just wanted to show you an example of animation. Let's move to the next slide, where we will begin the different components of the lecture. So I just wanted to let you know that, of course, all this information that we will discuss you can find it in chapter 10 of the Ewald book and the technical graphics part. But it also have kind of my own experience with how graphics can be used in different ways of communicating information, whether in a written format or in presentation. So I take some of the content from Ewald, but then I kind of modify it with some of my views on how to present this topic to you. So again, if you need to read it, I do strongly recommend that you go to this chapter and certainly to listen to this video from beginning to end, so that you get some ideas, and hopefully that will help you with your presentation and with your reports. So let's move on to the agenda of the talk. So the outline is as follows. So we will begin by discussing some of the function of graphics, and we'll do that as we go along. We will then also talk about the different types of and uses of graphics. So for whether it's a two-dimensional graphic, this is an example of a two-dimensional graphic. This is another example of a graphic, but this one is three-dimensional. You have your X, you have your Y, and you have your Z. Here you only have X and Y. This is another variety of a graph, and it's usually just the points. And essentially, this is useful a lot when you're trying to show geometries, for instance. In our field, we use this a lot in telecommunications, where every point they represent a person or a device, a wireless device. So this is referred to as a scatter plot. This is also used a lot in machine learning. So scatter plots are used a lot in machine learning. So machine learning is of course the very hot topic these days, and people use this sort of plotting as well. We will also discuss some of the different forms of graphic. For instance, this one here, this is known as a block diagram. So you have different blocks, and you have arrows that goes with the block, right? So you could see how it begins, and then you follow through the arrows until you go to the end, to some end points, from beginning point to some end point. So beginning point would be this and this, and then you enter into it, and then this as well, right? So this is an input, this is another input, this is another input, and then the output would be this one here. So this is an example of a block diagram, but there are others as well. We will also kind of go through a form of presenting an algorithm. And if you want to present an algorithm, you could use this with a flowchart. So perhaps you've seen this in other courses as well, some VHDL courses or other simulation courses, or Python or Java. You've seen perhaps flowcharts. And they are very powerful as well. So anytime you want to code or you have an algorithm, a flowchart makes sense, where they could take a decision whether, so you have some statement here, or some question, and then if it's yes, you do a certain thing. If it's no, you do something else. And then that's how you begin an algorithm, and that's how you end an algorithm. And mind you that sometimes people forget to realize that anytime you have a flowchart, you are able to put it in an algorithm fashion. So this is a way of showing a flowchart using an algorithm. So you could always go from flowchart to algorithm, or algorithm to flowchart, because at the end of the day, algorithm is essentially a flowchart, and a flowchart is an algorithm. So you could always move between these two regularly. So depending on the form of data that you're trying to present, perhaps one approach is more liked than the other, or perhaps you could show both of them. That's also a possibility. We will also show you and discuss briefly on tables, how to present your information in a table format, in a tabulated format, where you have a bunch of information there, and that's another way of showing your graphics. We could also you could also show your information by drawing. So this is referred to as line drawing. So you actually have a drawing of the engineering concept that you want to do. So in this case, you have a vehicle and you have a drone that comes on top of it. So this is from a patent that I found online. Essentially, in the patent, what they say is that what if an autonomous vehicle goes defective and some of the sensors in the vehicle are no longer working, let's say a LiDAR, then you could the company or an agency could fly in a drone on top of the vehicle, and now the drone will remain stationary, will remain positioned on top of the vehicle, and it will act it will basically replace the defective sensor. And so that's kind of an idea of that was proposed in a patent. So this is referred to as line drawing. You could also have pictures, right? So an actual picture of what you're trying to show. So that's also a possibility. So these are all different ways of conveying information graphically. So we'll go through some of them in this lecture. Putting graphics in reports will give you some hints on how to do that. If you've never done this, which I assume you've done this, but we'll just give you some hints. And we will use Microsoft Word. It is not the best. I've perhaps told you about this. It doesn't create the most attractive output of documents, but sometimes it's good enough, and therefore we'll show you with Microsoft Word. But certainly you could use other type of processing tools to convey your information. In particular, LaTeX is something that scientists and engineers use a lot, but Word should be fine as well. We will also show you the different way for avoiding graphical misrepresentation. So sometimes when you show some data and people are not too careful with the axes, they don't represent it in a proper way, that causes a lot of kind of misleading or erroneous interpretation of the data, and it doesn't get the message across in a proper way. So we'll show you how to be effective in this, right? So for instance, anytime you plot, you have to really explain what the x-axis is, what the y-axis is. This is one of the basic requirement of any plot that you have. Sometimes they show the x-axis, but there is no description, like here. But so of course this is not good. You always have to describe what this x-axis is, what this y-axis is, and when you're presented as an engineer, it is a good practice to always explain your graphs. Some people, when they present, and I've seen this a lot, they show a graph, but they never explain their axes. So as a good practice, the first thing you should do when you present any technical information, always show the graph explain the graph, introduce the graph, because looking at a graph is just okay, nice, it's cute, but it doesn't convey, it doesn't mean much, right? You have to tell us what it is. Tell us what you want us to pay attention to. So tell us what the x-axis is, what the y-axis is, and in case you have a z-axis, tell us what the z-axis is, the units that you're using, why you're looking at it from this perspective, and so on and so forth. Help the audience understand. So anytime you present, you should always describe your images, not just put it out there and assume people will get it. Okay, so let's go through the topics. So in this slide, we will talk on the function of graphics. So number one, you should realize that we're all visual animals. We understand better with images, with pictures. Like I said, the earlier quote from Napoleon de Bonaparte, where he said, "A picture is worth 1,000 words." Right. So that, I mean, at the end of the day, we want to help ourselves and also help our audience, help our target audience to understand some ideas, complex ideas. Don't forget that in our field, in the field of this, in the sciences in general, not just in our field, in the sciences, whether in the pure sciences or in the applied sciences, we will work with a lot of intricacies, right? A lot of data, a lot of ways that we get information, and this information has to be put in some fashion, has to be recorded somehow. And you could certainly record it in certain methods. But then when you record it, you have to make it understandable by others. And this is where graphics become very important. Even recording the data, when you record the data and you want to display your data, not necessarily graphical, perhaps you want to use tables, and therefore it's very important, right? So for us, this is very very important to look into this. So although this presentation is mainly aimed for engineering individuals, but I assume it could be useful for others as well, because graphical presentation is a commonality that everybody should have or will basically face, right? We use graphs all the time. So graphs present complex information at a glance. Right, so you have a lot of complex information and you're trying to present it in a very compact and short way. So you want to present it in a digestible, short way, and that's why graphs are very powerful. They show trends. So right away you can see the trend. Remember the earlier slide that I showed you from the work of Hans Rosling, where we had these bubbles that move along. So they showed us the trend with the moving of years. Right, so they show trend easily when you have graphs, particularly if you have animated graphs. Graphs, they show proportions effectively. So sometimes you want to show the different proportions, right? So for instance, even in the Rosling presentations, he had different bubbles. Some of the bubbles were small, some of them were bigger, and they show the proportion of, for instance, the amount of population per country, right? So and the same thing could apply in engineering disciplines. So graphs clarify complex relationship. By definition, a graph, especially if you have a plot, a 2D plot or a 3D plot, they essentially show you the relationship between one axis versus the other axis. That's the whole point of a plot, is to show the relationship between two different axes. And if you have three different axes, it shows you the relationship between all three. So Z, X, and Y. The relationship among them, and it's very powerful in that regard. Graphs also form lasting impressions. So when you see a graph, you could essentially get an idea, and then this idea, hopefully, it will stick with you. So it will be a lasting impression. So for instance, if you recall, in my work on V2V, I showed you a plot for the outage probability versus the Manhattan distance, and I told you that it's good to look at it from a granular point of view, and therefore you could perhaps remember that the empty part is in the middle between the bad and the good. So the middle is where the average happens, but in reality, every instance of the realization will never be in the middle. So perhaps if that's something thought of, it perhaps that could be a lasting impression for you. For me, when I look at these graphs, especially when we got the result, it was the kind of the key impression that it had on me. So it depends on which graph you're looking or which graph you're studying. It will keep a lasting impression, and anytime you will remember something, you will remember of that impression. So now that we saw the functional graphics, we will look here at the types and uses of graphics and some of the good practices and some of the not so good practices. Graphics should be as clear and uncluttered as possible to make them easy to comprehend. Sometimes we look at a graphic and it has information, and perhaps sometimes the information is too much. Sometimes we have to do that because we want to show all the different variables that were considered in the graphics, such as the ones that I used in my own work and on V2V, my own work and in the work that I had with my colleagues back at Chalmers. So we had a lot of variables shown there, but we tried to make it as clear as possible in a nice box to show all the variables considered. But in general, having a cluttered or graphic is not something that is desired. You have to make sure that the graphic is understandable by somebody studying it on their own, and also certainly understandable when you present it. So if you present it, it is always a good idea to explain the different critical variables that you considered in your graphic as you talk. This is an example of a graphic. So what you have here is you have basically perhaps a distribution. So you have, we call this in mathematics as a histogram, and it's a three-dimensional histogram. So you have the bins here for a certain range, you have another set of bins here, and so on and so forth. Now, what is missing in this graph certainly is the explanation. What is the x-axis? What is the y-axis? It seems like the y-axis is the frequency, the number of times the occurrence happened. But still, you need to describe what it is. So you have to explain what it is, the unit of it. If there's a specific unit, the same thing applies here. Now, if you look here, the representation of this graphic is in three-dimensional fashion. So you have an x, you have a y, and it's shown in a three-dimensional way. But there is no purpose why it is done this way. It could have easily been in a two-dimensional display, just shown in 2D, x and y. There is no point for the z. There is no values here. If there's no values, then just for the aesthetics of it, it doesn't add value to your presentation. So it is not a good approach, and this is basically considered as a bad figure. You do not need to do that. You could do this if you, for instance, had other set of histograms in the back for other purposes. Maybe this is for one type of application. You have another set of histogram for another type of application, and then you stack them together. Then you could add a third dimension. Otherwise, having this third dimension is pretty much useless in this example. So this is not a successful or a good figure. Different type of graphics excel best at presenting different kinds of information. So here, as you can see, there are so many varieties of plots that you could consider. These different displays come in from MATLAB. So MATLAB is a powerful tool that many people in engineering use to display their outcome, their work, their research, or their result, their output of what they discovered, whether from simulations or also from emulations sometimes, and so on. You could also input into MATLAB, for instance, data that you've collected in real life, and then use it to display your data in certain different formats that you have. Okay, so you have a variety of different plots that you could use. You have line plots, so essentially 2D plots. You have distribution plots. This is mostly important when we talk about distribution, so things that add up to 100%. You have discrete data points. So this is kind of like that. So essentially this is kind of very used a lot in digital signal processing. For example, you have geographical plots like we saw earlier as example of a geographical plot where we had the 3D projected on a 2D, and we saw that on the cover of this video. You have polar plots. This is also useful when for certain areas where you need to not only look at it from one dimension but multiple dimensions, and then the angle, the polarity becomes important. So this is another way. You have counter, vector, and so on. So there's a variety of plots, and in fact, the list is even longer than this. I just took half of the display that I found on their website. Now, MATLAB is only one option to do this. It's quite famous. A lot of engineers use it. Even people in industry use it, not only academics. But there are also Mathematica is another tool to plot. Excel, Microsoft Excel is another way to plot. Word and Excel. So these are also possibilities for plotting different displays. Okay, let's move on to the next slide. Moving along now, I'd like to show you another variety of displaying your information. And here we're not really using a graphical way, although sometimes the word tables is kind of a subset of graphics, but it's not graphical. It's not some image or some plot that you're looking at here. You are looking at the information, and in other words, the data in a tabulated way. So you have a certain table. I mean, this is a table. This is an example. And then you have rows and you have columns. And you could set it up in different ways depending on what you want to display. And sometimes you actually need to sit down, put it on paper, think about it to figure out what is the best way to display your information in a table. It's not always trivial that the first table that you build will be the most effective one. Sometimes you build a table and then you look at it the next day and you say, well, maybe I did not put it in an efficient, compact way. Don't forget, you want to be as compact as possible, and you want to remove any redundancies. You want to lower the number of rows and columns. So your aim is to be as smart as possible in putting your table together. So it's not always trivial, especially if you have many variables that move along. But in general, this is one example, and then you might have basic examples of tables. So align large amount of complex numerical information in rows and columns. That's basically the definition of a table that you may have in a document. Tables provide a snapshot in a tabular form for easy access and comparison. So as soon as you see this, you're able to compare. You're able to compare this set of data with this set of data and then with this set of data. And they all vary according to the value of W. So here you have a W of 8, 16, and 32. I don't know what these values are. These are just some example of a table, but it easily allows you to compare that. Certainly, it's still abstract because you cannot make total sense of it. You just see numbers in rows and in columns. So it's not necessarily the easiest way to comprehend, but sometimes you need to have a table, and therefore you will have a table. And then in addition to a table, you could complement that with figures. So that's just another variety of displaying. In technical documents, you will almost guaranteed you will always have some form of a table somewhere. So this is almost guaranteed. I mean, in my writing, every time I write something, I will always end up having some table. Don't create a table for the sake of having a table. The table that you add should add value to the writing. If you think that there is no point of putting a table, you could put your data meshed in the text, then just put it there. You don't need a table. But if you think it is easier for the reader to compare and to look at different things in a nice area where all the data is in one area, in one table, then by all means, go ahead and do it. But in general, you are not obliged to use a table. Use it only if you think it adds value to your document and it makes your document accessible. Don't forget, your number one priority, and perhaps I keep repeating this in multiple lectures, is to make your document, your presentation, your technical report, your paper, your manuscript, your white paper as accessible to an audience as possible. Right? So you have to identify your target audience and make it accessible. Tables are not good at showing the trends in the information. right? So if you want to see the trend, is it trending upward? Is it trending downward? Is it trending with valleys and hills and in different type of shapes that you might end up having if you would have looked at it from a plot? That's not obvious in a table. A table is just a bunch of numbers, so it's not always the best for showing trends, but nonetheless, it is still a way of displaying information. Okay, let's move on to the next slide. In here, what we will look at is a pie chart. So pie chart is one approach for looking at, displaying distribution. Distribution essentially is the way, so you could think about it. I mean, this is how I think about it. It's as though you have a cake and then there's different components, and every component will eat a bunch of your cake. So this is kind of what you have. So this is one component, another, and so on and so forth. So that's basically distribution. You perhaps have seen this in the probability and statistics course, or in the statistics course, the concept of probability mass function, PMF, or PDF, probability distribution functions, or histograms, where the distribution of an event is distributed according to a certain display. Or perhaps you've seen me when I post your grades. I always post your grade, and then I usually attach a histogram of how the performance of the class is according to some to a specific evaluation. And then that histogram shows how the grades of students is distributed along. So you'll see where the majority is. Usually, when the sample size is big, it should resemble a bell curve, right? A Gaussian distribution. But eventually, so pie chart is used when we can add things to 100. So like this one here. So pie charts are excellent for showing proportions of a whole. Right, so if we talk about the relative population of the Atlantic provinces, and we have Nova Scotia, New Brunswick, Newfoundland, and Labrador, and PEI, and we want to show the how relative what's the number of population for all these Atlantic provinces. So so certainly here you don't see my province, so my province of Quebec is not here. This province where I live and where we work, Ontario, is not showing here because it's not Atlantic. This is only the Atlantic one, and we want to know how big the number of people living there are. What's the percentage of people living there is compared to the whole Atlantic region. So Nova Scotia has the largest population. New Brunswick has the second largest population. Newfoundland and Labrador has the third share, and PEI has the smallest. So that kind of gives you a sense of how to look at it from a perspective of the Atlantic provinces, and you could see right away the share of each of these regions. So very quickly, it allows you to get the information that you wanted on the spot. Mind you, this data is a bit old. It's from 2011, so I'm sure the data changed. We're in 2020 now. So anyways, pie charts should always add up to 100. So if you do the math, 41 plus 31, that's 72, and that's 80. So that's 72, and that's 74, and that's 94 plus 6. That's 100. As you notice, I'm not the best at math, but yeah, so it should add up to 100, and this is the same thing that should apply when you look at distributions. Now, the only difference is with a PDF, it's a bit different because it's a probability distribution function. What is below the graphs that should add up to 100, but that's just a side note. Generally, pie charts, they begin with the biggest piece of the pie at the 12 o'clock position. So 12 o'clock position is here, and you look at the different parts. The one that has the biggest chunk, which in this case is this part here, the Nova Scotia part, it should begin at 12 and take whatever share it has. So it has a share up to here. not more. But you always begin with the biggest one at 12 o'clock. So that's just a good convention to use when you use pie charts. For emphasis, a pie piece can be pulled out of the whole. So for instance, in this example, we have, so you have a bunch of animals in a certain setup, and frogs, hogs, dogs, and logs. And let's say we want to focus on the hogs, right? So we just pull this one out of the pie chart. In other words, we're trying to highlight that we are mostly interested by this one here. And that's why we pull it out of the whole. So you could do that as well, and there's ways to do that as well. So this is a pie chart, and let's move along. I just want to show you one more slide on pie charts. So sometimes what you want to do is you want to show a pie chart, but you show it with with kind of in a three-dimensional way. So you add this kind of elevation as well. And that's okay, right? So 3D graphics provide more visual interest. It makes it visually more interesting. But sometimes they don't make the information more accessible, right? So you're not adding more value by putting it in a three-dimensional way. Don't forget that when you're presented like this, suddenly your figure is no longer facing the reader. It becomes a side view. You're looking at your pie chart from a side view. So it's visually cute, but it becomes sometimes harder to see. So for instance, angles makes the small pieces harder to see. So certain pieces, certain regions are harder to see when you look at it from an angle. So this is just something to be reminded of. Best reproduced in color for greater contrast. So you could decide on the color that you want to use, so that when you print it, it shows up properly, and also because it is placed in an angled way, so that could also play a role with that. So you could play with different colors and look at it, and then ask your colleagues to see what their view is. But if you want to be you want to have a safe choice, then you could certainly put it in 2D. I have to say that for me personally, I don't mind seeing certain pie charts in 3D. Sometimes they are visually more interesting. So use it according to your taste and according to what you think your audience or your target audience would like. By the way, like we said, always the biggest chunk should begin at 12. And then the next biggest chunk should be next to it, the third biggest chunk, and so on. So here, this is not followed properly. So the biggest chunk, the hydro part, is certainly here. It begins at 12. The one after that, it should be coal, and that's fine. But then the one after that, it should be nuclear, right? Because it's 12. And then after nuclear, it should be natural gas, and then oil, and at the end it should be the 2%, the other. But perhaps they did it this way because of graphical and arrows and so on. I don't know. But in general, that's the convention that you want to follow. The same thing applies with earlier, with that slide that we saw with the hogs. The hogs and the different animals, the chart wasn't done in the convention that we said. Always the biggest chunk began at 12, the second one next to it, the third, and so on and so forth, until the end where it becomes really, really small. So that's kind of the natural convention, so that you are, again, aiding your viewer or your reader or the whoever is attending your talk to follow in a coherent way, from biggest all the way to smallest. So these are things to be kind of reminded of as you build or use pie charts. Now, at this point, we will look at the bar graphs and column graphs. And in the bar graph, what you see is you have an example here where you have the different bars that are placed in this fashion. So they're horizontal. You have the description that you have here. And then you have whatever metric you have here. So for instance, in this case, the metric that they're considering is cents per kilowatt hour. So that's the generation cost. You have another example, which is a column graph. So the bars or the bins that you have, they are placed in essentially in columns, right? So they are vertically placed, and you have that. So you have the description here, and then you have the values here. So depending on which one you think is easier for your audience or for your target audience, you could opt with one approach, bar graph as opposed to column graph. But this is really left at the discretion of the writer of the document or the presenter of the slides. So bar graphs and column graphs, they provide quick visual comparison of quantities. They don't always add up to 100%. Although you look at this and you might say, well, hold on, it does remind me of a histogram. So it does remind you of a distribution. And you might want to use that for a distribution. So you would think that because it's a distribution, it should somehow the density of it and the quantities, when you add it, you divide by the total number, it should add up to 100%. But that's not the case here, right? This is just a plot. It has nothing to do with distribution. So it is not a PDF, a probability density function, or a PMF, a probability mass function, or histogram. It is just a column graph here. But it looks like it, right? There's bins and so on. In bar graphs, bars originate at the y-axis. In column graphs, they originate at the x-axis. Right? So in bar graphs, they originate at the y-axis like this, so horizontally. And in the column graph, they originate at the x-axis and they are vertical. So this is just some description here. Okay, so let's move on to the next one. So in here, we look at line graphs. So here you have an example of a line graph. You basically have a plot. You have the emission, the CO2 emission, and over years, right? And then you have the different the reasons for or the different attributes of each line. So this is also the title of your figure. By the way, if you add a figure and your figure is added in a written document, this description could show up in the caption of the figure. So you don't need to have a title for each, unless you think it will help the reader. But if this description is redundant with the caption that you add, for instance, when you add figure, I don't know, 2, and then you add the description of it. If this description resembles this, then that's redundant and you don't want to do that. But if it adds more value, or if it helps the reader to remove any confusion and it is not redundant with the caption, you could by all means add it. Otherwise, don't do that. So here, line graphs, they show trends over time. Right, so it does sometimes. Time is literally time. I mean, this is time, this is year, so it's really a measure of time. But sometimes the x-axis could be anything, right? It doesn't have to be time. It could be any value that you're working on, right? So that's just basically what it says is it shows the trend as you move along, depending on what metric you use for the x-axis. Lines can be stacked to compare trends for multiple values, right? So this is a figure and you have multiple lines here. You have one line for other purposes, you have one line for mining and oil gas extraction, you have one line for manufacturing, and you have one line for utilities. You don't want to do 4 different graphs by themselves and just one line in each graph. It's hard to compare. When you put all these different lines together, you stack them together, you are then able to compare. You're able to compare, for instance, oil and gas with utility. Which one has more impact? So it's easier to compare when you put it all together on one figure. And you want to do that. You want to be smart when you create your display of information. You want to use as less as you want to be compact in your display of information, and you also want to be accessible. So you want the reader to be able to quickly have the capacity to compare and contrast with the different possibilities of whatever you're displaying. So this is one option, this is another option, third and fourth. I'm able to compare them right away, right? It helps me. Whereas if you had 4 different graphs, it's hard to compare. Although you keep the scale the same, it's still hard to compare. You want to put them all together on one plot. So this is where this stacking comes into play. You could also have lines that are stacked cumulatively. And this is what's interesting here. Cumulatively is not like this. Here you might have overlaps, right? So this line somehow overlaps with this. They are independent, these lines. They are not necessarily dependent on each other. They're independent, and that's how you put it. Whereas in here, each line is placed in a cumulative way. right? So you have, for instance, the fossil fuel has the biggest chunk. It's this one here. The nuclear is the second, so it adds up to whatever was left by the fossil fuel, and then the renewable is added to both of them. So these lines can never overlap. You can never have this line and this line overlap on each other. Overlap is not possible in a cumulative stacked way. So this is also another type of display that could help visualize what you're trying to say. It always depends on what is your message. What are you trying to get across to a reader or to an audience listening to you? Depending on what your aim is, you have to decide on which option of plotting you want to go with if you're considering line graphs. Okay. Of course, the most kind of commonsensical way to show graphs is essentially the actual live picture, an actual picture of what you're trying to show. So you have, for instance, this picture. This is a picture from CERN, from the Hadron Collider in Switzerland and neighboring countries. So that's that. And you also have another picture, a picture of automation. So you have these automated robots that are trying to in arms that are trying to assemble something, probably assembling a vehicle or some other electrical device. So that's an actual picture that you take with a device. Now, photos show the greatest detail and have the greatest accuracy because you're really taking something that is built and you're showing it. It doesn't mean you will always have actual live photos. Sometimes you don't have anything to display, right? So it is a concept. You're at the conceptual phase, and you're coming up with an idea. You could show some photos that existed to show how you're inspired by them, but you have nothing to show. You are trying to build a prototype. You don't even have a prototype. So that in that case, you will probably use some drawing that you have. But if you have an actual photo, then that's fine. But be mindful that photos may be difficult to focus the viewer's attention on specific detail. You look at this CERN Hadron Collider, I'm not sure what I'm supposed to look at. Am I supposed to look at this guy, how tiny he is, and this huge engineering marvel that is used for physics? Or am I supposed to look at these pipes? I'm not sure what I'm supposed to look at. I just see it, and I'm not sure what am I supposed to focus on. If I look at this, I see some automation device here, but I'm not sure what it's assembling. It's hard to focus on. So if you want to say something generically, that's fine, but be mindful that it could be difficult to focus the viewer's attention. So if you put a picture and you think it is supposed to be there, it is adding value to what you're doing, explain why this picture is important to the audience if you're presenting. If you have this in a written document, really you need to have a strong argument why you want to add a picture. Sometimes I see students, they write me a technical report, an engineering technical report on some case study, and then they put in pictures. And I tell them, always ask yourself, is the picture adding value? If the answer is no, it does not add value to it, why put a picture there? I had a student. The student worked on cars or some component to a car on electric vehicles, and they added a picture of a car, just a picture of a car. Now, I think we all know what's a car, so adding a picture of a car will not add value. If you're adding a picture of a car that has an EV component to it and you want to show where the EV will be within the car or the various subcomponents of the electric vehicle that is used, where it's placed, the cells, and so on, then you could certainly add a picture there. But if it's just a picture of a car, that doesn't add value. We all know what's a car. So always ask yourself these questions before adding it, adding anything to a document. So that's for that. Line drawing is another possibility, and perhaps line drawing is you would do that when you actually have nothing to present. You're just showing a concept of something that you aim to build on, or a concept of some some work that you aim to build, and so on and so forth. Or perhaps you actually have it, but it's in prototype phase. It's messy. There's wires sticking out everywhere, and you don't want to show that display. So you would kind of represent it in a line drawing. Or perhaps you have it, you manufacture it, but you want to put more explanation, and you believe that drawing it is nicer for the presentation. So the different reasons why you would opt to use line drawing, and you have some examples that I placed here for you. So you have this example, a hydraulic example, and you have this example, an autonomous vehicle with a drone. So line drawing simplify images by getting rid of the details and surfaces, right? So it kind of simplifies a picture, and it keeps the attention of the viewer, or the reader, or a target audience in a presentation, to the specific things that you want to discuss. So in this case, I know that what is important here is this, right? This component here, which we call a drone, and that's the key thing, and also the fact that this is an autonomous vehicle. In the relationship between them, and this is used in a patent, whereas this is a hydraulic system. You have all the different components for a hydraulic system, from the bracket to the valves, to the vent, and so on and so forth. Okay, so line drawing focuses viewers' attention on important details such as installation components, right? So you could kind of keep the focus on that. Yeah, so it is generally a good practice to use line drawing, especially when you write documents and you are trying to explain the different components in a document. I think it's always easier to not put an actual live picture. Assuming you have an actual live picture, line drawing would make it easier to help the reader only focus on the key things. So in this example, like I told you perhaps earlier, this is a concept that was proposed by Ford. And this vehicle is an autonomous vehicle, and they have sensors in the vehicle. I'm not sure if it's on top or other places, but let's assume they have a sensor. Usually with autonomous vehicle, you have the key sensor on top, the LiDAR on top, that kind of builds a map of your surrounding. And in this case, the assumption is that the other sensors, whether it's computer vision sensors, or the LiDAR, or other type of sensors, ultrasonic sensors, other type of sensors, are defective. And in this case, the drone is flying. It gets positioned on a car, and it acts as it replaces the defective sensors, right? It will act as the sensor until the vehicle is brought to some station where it could get serviced, and its sensor gets repaired. So in this case, we know that the key thing in this proposal, in this patent proposal, is really the landing of a drone on top of a vehicle. That's it. Right? Or perhaps the vehicle is moving. The landing of a drone on top of a moving vehicle that has defective sensors. Okay, and that's why most of the arrows, they point at the drone, and that's the concept that was proposed by Ford. So that's kind of an example that you see of line drawing. Diagrams are also another set of very powerful approaches for displaying some graphic of what you want to work on. So in this case, you have an example of a mobile phone. So you have a phone, an iPhone. You see here, and then you see here, so you know it's an iPhone, and it's referred to as an exploded drawing of a device. And what the benefit of this display is that it shows the assembly sequence. It shows how the different components are assembled. So this is a very neat way of doing that. Of course, it's hard to identify the different components if you're not too familiar with everything. So in addition to showing this kind of view, an exploded drawing view of this mobile phone, you could perhaps also add arrows with description to tell us what each component is. And it's just a very neat way of showing how the device is assembled. You might also see things like this. So this is referred to as a cutaway reveal. So it's a cutaway view of a vehicle. or it could be anything else, right? So whatever electrical or mechanical gadget that you're studying or analyzing. So it kind of, so of course, you have the different metallic part covering your vehicle, but it's shaded out so that you could focus on whatever the attention or the study is on, right? So you have your engine, and then you have all the different components for the suspension and other parts of the vehicle. So everything else is shown. So it's a cutaway reveal that reveals the inner workings or locations of internal components, and that's another diagram, to show the to show that. Okay. Flow charts and schematics are also very important. So schematics for us electrical engineering people, we will use this all the time. You have this in multiple of your courses, including some courses that you take with me in electrical fundamentals and with other professors. Flow charts are very critical. As we said, almost everything that you do in terms of coding, or even not necessarily coding, but in general, anything that has some coding component or some algorithmic component to it, it will generally be represented in a flowchart format. So this is an example of a flowchart. You have a beginning. You have different kind of logical way to go through the process until the result is spit out, right? So you begin, and then you get the result. So in this case, this is just an example of summing. Find the sum of 5 numbers. So how do you find the sum of 5 numbers, and what's the logical way of doing it? Flowcharts and schematics are a conceptual representation of processes, organization, data, and the like. Mostly flowcharts as opposed to schematics. Schematics are used for specific areas. So flowcharts, so they're called flowcharts when an actual movement is implied. What do we mean by movement? Is that you begin somewhere, and then you move along, and then you have to ask yourself certain questions, logical questions that are related to what you're doing. So, is the count less than 5? If it is less than 5, then you move along and you go through this loop, right? This for loop. If the answer is no, then the result breaks from the loop, and then you simply get the result. So that's kind of what we refer to in a movement. So you begin somewhere, and then you move all the way to the output. Right, and we said this, as soon as you see a flowchart, you know right away that this is an algorithm, and if you prefer, you could in fact write it in an algorithmic way. And when you write an algorithm, you basically have different lines of written text. In it, you'll have some approach of writing your code, and this approach is probably you've seen this is referred to as pseudocode. Right, so you are writing a code, but this code is not Python. This code is not C. This code is not C++. This code is not Java. It's a pseudocode. So any person reading it using whichever language they prefer, they'll be able to implement it, because it's just the flowchart. As you see, the flowchart is not written in Python. It's not written in MATLAB. It's not written in C++. It's just written in a flowchart way, and that's it. And the same thing applies with an algorithm. It's just written in a pseudocode, and so anybody could understand the algorithm or the concept, and then type it in the language that they're working on. So it's not a bad idea to always go from a flowchart to an algorithm, or from an algorithm to a flowchart. Usually an algorithm looks nice when you want to publish a work, or when you want to create a document, a written document. A flowchart is usually opted to as a display when you are trying to do a presentation. So if you do a presentation and you show a pseudocode, it's not necessarily effective. Whereas if you do a presentation and you show a flowchart, it's easier to comprehend, it's easier to follow, it's more visual. I could right away see it. And in fact, if you build your flowchart with the audience, if you have the time, so with every click something of your flowchart appears, then you could do that. If you have a long, big flowchart, of course, don't do that. Just show it, and then always refer the reader to the paper, or to the document, to the white paper, to the technical report, whatever the case might be, to the book chapter, to the book, and then they will get the rest of the information there. So that's just one approach of doing that. Schematics, well, this is a schematic, so we see this everywhere in our discipline in electrical engineering. So you have your AC source, you have a bunch of resistors, you have your transistor, you have your VCC, and in this case you have also different capacitors. So this is a bypass capacitor that is installed here and so on. So this is referred to as schematics. You could do schematics in using different tools that we have at Sheridan. For instance, Multisim is a typical approach for using for building a schematic. We are also trying to get other easier tools to use to build a schematic and to test your schematic, because right now we are not doing in-class teaching, or because of the COVID situation, and so we want to focus on simulation-based work. We do have Multisim for sure, but we're trying to get other tools as well, and we'll let you know accordingly. So that's this is referred to as schematic. Okay. This is a part that I'm sure many of you are familiar with. You've done it before, but I still wanted to go through it very quickly in case some have not seen this before. So how do you put a graphic into your report? So let's say you could essentially have some visual, some graphics that you've done independently and using some other tool, let's say Visio or MATLAB or whichever the case might be, and now you want to add this to your report, or perhaps you want to build this right there and then on the document that you're using, right? So in Word, you want to build it, you want to create your graphics there. So you have both possibilities. So we'll just show you this very quickly. So you open your Word application, and in there you go to the Insert tab. So you could click the Insert, and then you will have the options you'll have different sections within the Insert ribbon. So in here, if we look at this place here, so you have the possibility to pick any of these options. So if you have your own image that you want to add, you've created it before, you could click this. You could put in some shapes, or you could also apply a chart, right? So a chart, some of the different charts that we want. So in this case, we'll go with this option. So we'll go with charts. And in the charts, you have the different possibilities of charts that you could use, right? So whether column, line, pie, bar, so on and so forth, right? So in this case, let's say we pick the pie chart. And that's why we selected the pie. And then we have different options of how to display it. Now that you've selected the pie chart, you can actually personalize it depending on the design that you prefer. So you could kind of change the aesthetics of your pie chart here. So you have the option here in the design tab for the pie chart. And of course, to change the value that you have, you could do that with the insert of your pie chart. So it will open a spreadsheet, an Excel spreadsheet, and in here you could just enter the description that you want. So like we showed earlier, Nova Scotia, PI, Newfoundland and Labrador, and New Brunswick of course. And then in it you could just enter the population or the percentage, and it will build your pie chart. So you have this possibility to do it here. As you can see, you're building everything straight inward. So this is it. It's a bit hard to show you all this in 1 or 2 slides. It is something that you really have to play with it to understand it, right? So the more you play with it, the more you interact with this tool, the more you adjust the interface of it, and then you modify the values, you'll get a better sense of how to use this tool, and you get a better sense of what is the best way to display your result. Is the pie chart the best way to display what you're trying to say? I don't know. It depends on the case, right? So you really have to kind of experiment with that and see what format of displaying your result makes sense. This is a a process that will require a lot of iteration. So you might consider one approach for displaying your result, and then you come in a week later on, a week after, you come in and then you look at your report and you say, well, you know what, maybe this way of displaying it does not make that much sense. Perhaps I could use this newer approach of displaying it. So you could certainly do that, and you get a better sense of what is best for your readership. Don't forget, your number one priority is your readership, or those in your audience. You are trying to make this as accessible as possible. Okay. Now again, what we want to show you is how to insert a table into your report using Word. Again, it's very similar to the approach by which you could insert a picture, an image, or a chart. You go to Insert, and then from Insert you locate the table. You press on Table, and then you could just select the size of the table that you want. Right. So sometimes you will pick a certain size, and then even after being displayed, you could, and maybe you decide to increase another row, you could always do a right click, and then it will give you the option to increase another column or another row. So you have the option to modify it after it's on your sheet. But this is kind of the general basic way of doing it. I assume everybody have already done this, but in general, if you haven't, then that's the approach for doing it. You can of course change the column width, and you could simply kind of come into the border of each of these columns, and you could do that, and you could do the same thing with the rows as well. So that's a possibility, and you could also activate the ruler by looking at the icon over there. Now in this part, we want to talk about the coloring of graphics. Color graphics looks great because of the visual appeal and the contrast to the text that you have in the background. So typically your text is written in black, unless you change the color, which is not recommended. You should in general stick to black when you write your text in a written document. In slides, it depends. It depends what you're trying to do. In slides, sometimes you want to emphasize, so you might change the colors, but be mindful that the colors in the background of your slide should be in a way that it will not harm the viewer. So choose the colors carefully. Sometimes the background has a very strong color, and the text is in a completely different color, and looking at it really hurts the eyes. So you really have to experiment and see which one makes sense. I usually use a white background in my slides. I think it's quite effective. It helps to focus just on what's on top. I don't put any design in. That's how I like it. But it's your choice to do that, because the focus is really on the text and on what you want to show. In a presentation, ideally you want to show the natural color of whatever you're trying to display. So you don't need to put it in black and white. But in a print version, so anything that you offer in print, whether it's written documents, even slides. Sometimes you present slides and prints. You have to be careful when you have colors of a picture. So colors are grayed out by black and white laser printers, so don't forget that. In general, the default setting of any printer, of any laser printer, is black and white, right? So you don't want to use color all the time, because it consumes that and color is more expensive. So you want to be more careful with this. And if you do print it in black and white, you have to make sure that what you're trying to convey does show up properly. If it's not, then you have to either change the shade of the gray or do some different testing and to figure out what makes sense, or perhaps just use a color printer. So this is something to be mindful of. If you're not in control of the output of the printer, you cannot control the output of a printer. Somebody else will print it on your behalf. The organization will do that. Check that the colors is still contrast in black and white. So let's say you put a colored picture or document or figure in your writing, and the printout will come out in black and white, because the company is trying to save money, not to use too much color. Just test it on your own. Just make sure that when you have a colored and it's printed in black and white, does it look okay? If it doesn't, just put the original picture originally in a gray scale, and perhaps that would solve the solution, or change the shade of the grayness of it. So just to make sure that this is it. So here, basically use your common sense, depending on what the case might be. In the end, you want, again, we're trying to always be mindful of who is going to read our report, who's going to see it, and we want to make this person happy, right? So if you put something and then it's printed out in black and white and he can't see anything, then that's not going to work, right? So sometimes I do peer reviewing work, and then people send a lot of graphics and all of that, and I don't have a color printer. I have one in the office, but right now we're not in the office. I'm at home and I don't have that. So it's not. And if I print it, I don't look at my machine, because I want to write comments and I want to take it with me as I'm reflecting on it. Whatever they're trying to convey will not show up properly. So people have to be mindful of the importance of color in graphics. Okay, if not, create your own graphics in black and white in the first place. So that's the comment that I just said earlier. So this slide is really common sense. So basically, just use your common sense when you have colors in any figures that you consider. Now, there are certain rules that you need to be mindful when you incorporate graphics. And these are very important, so please pay specific attention to this. I've seen some of the reports that come in from students, and they fail to take note of these two items that we want to show here. Number one, every graphic should be introduced or referred to in the text of the report. Sometimes what students do is they include a figure, but the figure is never mentioned in the text. You should always refer. If you include a figure, you have to make sure that you include it in the text. You have to tell the reader close, right, in the text that is relatively close to the vicinity of where you place the picture, or the figure, or the image, or the block diagram, or the flow chart, or whatever the case might be, the plot. You have to tell in written format within the text that you are discussing or you are talking about something, and this is better explained in this picture or in this figure. You have to mention somehow the figure that you're using in the text. This is very important. You cannot just include a figure, an image, a diagram, a flow chart, a block diagram, an algorithm, a plot, and not mentioning it in the text. You have to mention it, and ideally you have to mention it in its identifier. Now, how do you identify figures? You identify figures using caption. So every figure, table, block diagram, algorithm will have a certain caption, will have a certain identifier, and they're numbered sequentially, right? So your first table will be table 1, your second table will be table 2, your third table will be table number 3, and so on and so forth. Your first figure will be figure 1, your second figure will be figure 2, your third figure will be figure 3, and so on and so forth, right? So you have to, these are the identifier. And every table, every figure, every flowchart, every algorithm will also have a title. So you need to come up with a descriptive title, right? The title should tell us what this is in 4 to 5, perhaps six words, not more than that. What are you trying to do here? Sometimes it depends. If your figure requires more description, you will have more description. You can't do anything about it, right? Ideally, you want to stick to 1 line of caption, but sometimes you might go to 2 lines, sometimes 3 lines. Sometimes you see this in scientific papers. Not necessarily the best way, because your caption should be relatively short. It shouldn't be too long. So caption, it helps those who flip through a report looking only at the graphics. So remember when we said that many people will scan a document. They will not read a document. Engineers are very, very busy people. I would assume the same thing perhaps with other disciplines as well, but in general, engineers are very busy. They don't have time to look at every single document, read every single page, every single word. So what they generally do is, number one, they look at the title. If they like the title, they will move on to the next thing. They will look at the abstract. If they like the abstract, they will move on to perhaps going through some of the images in the figures, in the pictures, the diagrams, the flow charts that you have in the document, in the paper. If they like that, then perhaps they will then move on to read the conclusion to see what is the big picture here, what is the key result. And if they like that, they'll go to introduction and read the entire thing. So there's a lot of points where you are trying to find a hook with your readership, with your audience, with your readership, and depending on how you're effective, people will either continue reading your document or they will just let it go. So when you scan a document, one of the things that people generally look at after the title and the abstract is really to look at figures. This is what I do. So if I'm looking for a paper, the first thing I do is I look at the title. If the title attracts me, then I'll go read the abstract. If the abstract attracts me, then I'll go flip through it and look at the figures and look at the pictures. If that attracts me, then I'll read the conclusion, and then if that still attracts me, then I'll read the entire paper. So that's my way of scanning a document. And so, like we said, when you scan a document, you go through it in very quick way. You simply look at the figures, and that's the scanning. So if you have caption, you have description for each figure. That helps in during the scanning of your document to understand what you've done. Having a caption, those captions appear in the list of tables and figures. Remember, we said that when you write a document, you generally have your title, your cover page, or your title page. Generally, it's referred to as the cover page. After that, we said you need to have your abstract and your keywords, and then after that you have your table of content, and after table of content you may have also a list of tables, a list of figures, and also the acronyms and the symbols that you use, the mathematical symbols and others, before you begin the writing. So you will need to create a list of tables and a list of figures, but in general it is a good practice to do that only when your document is of reasonable size. So if your document is more than 10 pages or more than 15 pages, you could include a list of tables and figures. If your document is less than 10 pages, it's not worth to include a list of tables and figures. Also, if you have, I would say, more than 5 tables and more than 5 figures, include a list. If you have less than 5, not worth including a list at all. So it would be silly to include a page with a list of tables and figures. So that's a minimum kind of a rule of thumb that you could use. But if you have caption, it will appear here. Use words caption function to automate captions and list tables and figures. So as we said, we're using Word here, so we'll show you how to build or how to annotate your figures with captions, and the same thing would apply with tables and with figures. So we'll show you how to do that on the next slide. So here we show you how to add the caption to a figure. So let's assume you already inserted a figure, as we saw earlier. So you inserted a figure. This is the figure that you inserted, and now you want to add the caption. So what you do is you go, you select the image that you have inserted. You simply select it. Then what you do is you go to the references ribbon here. And then once you are in the references ribbon, you click on the insert caption button. So you have it here in the captions part here of the references ribbon. Okay, and once you do that, the caption dialog box will appear, which is this. This is the dialog box that appears, and suddenly you see a number. You see a number. This is generated automatically. Right, so this number that you see, 17, is generated automatically. Basically, what it means is that you have 16 other figures that are inserted before that, and they have captions. So this is the here, and then you could just add next to it a title. You could add a title accordingly. In the future, if you decide to move your figure, the number is changed automatically, right? So as written here, so the number will be filled automatically and will be renumbered automatically if you move the graphic around or insert other graphics before this one. So let's say you decide to include another figure earlier on in the figure, then everything will be shifted by 1, so this will become 18 automatically. So all this is done automatically, and it's quite useful to know how to do that instead of doing it manually. Also, remember that, or perhaps not remember, I should mention that when you put the caption for figures, it should always be below a certain image or a diagram or a flow chart or a block diagram. Always below, not above. Above is only tables. For tables, you put it above a table. For figures, always below. So just be mindful of that. Finally, we're at the last slide of this lecture, and it's related to the axis values. So we said when you plot, whether it's in 2D or 3D, you have a certain plot, you have your axis, right? And the values on the axis could sometimes be not represented in the proper way. Right, so I'll show you what I mean in a second. So imagine you have this representation, right? So you have this plot, you have, it looks like a histogram or bars that you have, a bar plot. And essentially what you see here, a column plot, and what you see is you have an x-axis and you have a y-axis. By the way, I should mention that this is also not the best. You always want to have an arrow. This doesn't show an arrow, so this is something that I personally don't like. So you need to make sure that it shows an arrow, but let's assume it's there, so that's fine. You also need a description on the x-axis. What is this? What is this? What is this? We have no idea what it is. You need to describe it. And the same thing on the y-axis. You need to have an arrow, and now you see the values. Now, if you look at this, it's a bit... I mean, it's a real result. You got a result. You have two events, and you got the result that you got, and you want to display it. But displaying this doesn't give us a lot of information. I mean, it does tell us that they're more or less the same in this view. So it's not clear what we want to say here. So it's not. I would say that this is not a great way to display a result, right? So an alternative would be, for instance, to zoom in. You could zoom in on the y-axis. You could keep the x-axis as is. The y-axis, you zoom in, so you expand it. You zoom in, so you have it kind of expanded like this. And the display that you get is this. But now this is also not the best, because this from this arrow, you know that this size is equal to 100. And you would assume then this thing here is also 100, so this value here should be 200, but it shouldn't. It should be very close to 100. So this is not the best choice. You need to have some value here. Your value is not shown. You need to have some value here. Your value is not shown. This is not a good display of a graph. So you tried to zoom in, but you didn't put the values of it. You didn't put the value here. You didn't put the value here. You just expanded it. You just took a picture here and you added it in this area. You tried to be effective by zooming in, but the result was not good, right? It did not convey what we want to see here. Alternatively, what you could do is you could have something like this. So you could essentially do a zooming in. You could magnify this area. You could magnify it, but as you magnify, you are also showing the ticks of your y-axis, right? So these are called the ticks of your y-axis. We know that, for instance, this is 98, this value is 100, and this is 102. So now if I look at this, and assuming there is an arrow here, there's an arrow here, there's a description for the y-axis, there's a description for the x-axis, this is identified, this would be considered an okay graph. This is considered okay if all that I mentioned is done. But you could certainly also improve it, or you could certainly have another version of it, which is something like this, right? What you have is essentially the same thing, except that instead of beginning at 98, you still want to have your 0. But if you include 0 here without putting these kind of like an electric shock symbols, it would not be to scale, right? It should look like this. It won't be to scale. It would not make sense. It would be as though saying that this is 100 and this should be 200, not 102. So you could have this, but to say that the rest is not shown, this part, you could just include this kind of like an electric shock symbol. So basically means that we chopped it, we cut it, and we showed the bottom part. We didn't show the middle part, and now we're showing the top part. So this is fine, and this is fine. You could use both conventions if you prefer. So this is good. This is good, this is bad, and this is bad. So just be mindful of when you try to enhance your display of a figure, it should also be logical. You can't just magnify this area and get this and give it to people. This is misleading. People will think that this height is the same height here, and therefore they expect this value to be 200, but it's not 200. It's only 102. Whereas this is fine because you put the ticks accordingly with the magnification, and this is fine too because you begin with 0. The scale may feel misleading because all this is only 2 values, and then this is 100 because, and it's 100 because you chopped the figure here, and that's why you included this symbol. So I went through this explanation twice. I hope it's understandable. So these two are good, these two are bad, and I hope that that helps you when you put together your figures. So that's it for this lecture. This should cover it for today. This is a 1.5-hour lecture, so that's covered so far. And that covers it for this semester. We have nothing else to cover. We've covered everything that we wanted to cover for this semester, despite losing that week due to COVID. But we covered all the content for the semester. What is left at this point is really an explanation of EVB. So I'll do that, and potentially I might also include a video for that to explain you how you will do your deliverable for EVB. This is worth 25% and it's due next week on Friday. So I'll explain that, and that concludes the semester. So you only have that deliverable, and then you are done with the semester. Thank you so much for your attention. Good luck with your studies and with your finals, and I'll update you with EVB shortly. Thank you.